Hello. Today's project is the Gigatron, a brand new, as of April 2018, just on the market, a retro vintage, well, I don't want to call it a microcomputer, but it's definitely a small computer. The manufacturers call it a microcomputer. It's based all on discrete TTL logic. It does not use a microprocessor, so the processor core is built out of discrete ands, ors, and latches and so on. There's the photo from the website. The kit costs just under $200 US, and it's ordered from the two fellows in, I believe it's the Netherlands, who produce this. And when I found out about it, I just couldn't pass it up. It looked like a pretty cool thing to build and to play with. So this video is about the building and demonstrating of that little computer. And the website, by the way, is gigatron.io. The Gigatron kit comes with a very nice manual in English with all the Heathkit-ish type of manual assembly instructions, and a vintage game controller for the games which are embedded in the firmware, and a nice presumably hardwood case with a plexiglass front, and all the necessary parts except for a power supply. So you've got all the discrete components, a small USB cable to power it, all of the ICs laid out in approximately the position they are on the circuit board, and then the one and only circuit board itself. Very nicely done. If I can not an extremely high chip count on this, but still quite a few chips. Just a quick overview of the board. You've got your power section, the blinking lights, which are status LEDs. This does have an audio output. It's a 4-bit D to A converter, just done with a few resistors, and gives you rudimentary output. There's the resistor set for the VGA color generation. The clock generator circuit. There is an RS-232 type serial controller connection. This is used primarily by the game controller, although I believe it can be used for communications with another computer. And then the logic that supports that. The program counter, again built out of discrete logic. The largest chips on the board are the RAM and the EEPROM. It uses a 74C1024 EEPROM, and then the RAM uses a 62256. So that's LSI, but as far as the functionality of the computer, the rest is all done with discrete logic. The result bus, the X register, low and high address, the Y register. This is the arithmetic and logic unit. The accumulator, extended output. This is the instruction decoder. It's done with diode resistor logic. The control unit, a AND gate built out of diodes and a resistor. So diode resistor or resistor diode logic. Apparently they needed one more gate in that position and didn't have a chip for it, so they just built it. I've been known to do the same thing in some of my designs. The addressing mode decoder, the various condition decoder, let's see, instruction register, data register, bus buffer, program memory. I think we've covered the whole board by now. So the one thing the kit does not come with, and it's not really necessary, but I like to have sockets on my circuit boards. So I ordered up a set of sockets from DigiKey and will be including those in my build of this kit. For those watching at home, here are the DigiKey labels for the IC sockets I bought. We'll start out with the 14 pin if I can find it. Here we go. So this is the 14 pin. These are all Milmax parts. I often use Osman and also Milmax. In this instance I found better availability with Milmax, so I went with them. And these are all gold flashed screw machine or machined type sockets, so they're not the cheap ones. So there's the 14 pins. Here's the 16 pins. The next is the 20 position. The 28 position for the RAM. And the 40 position for the EEPROM. So there are all those IC sockets. And if you were studying the labels closely, you'll notice that I, with the exception of a couple of the ICs, such as the 28 and the 40, I ordered a few spares just to bring them up to round numbers. Always can use a few more in my parts drawer. So before I get started with the assembly, here's just an overview of the manual. And this is very nicely printed, spiral bound. Has an introduction, table of contents. Talks about how in 1975 Steve Wozniak famously designed the Breakout arcade game out of 44 simple chips without using a microprocessor, simply because those weren't available to him at the time. But within a year the MOS technology, or the MOS technology 6502 and the Zilog Z80 were introduced. The 8080 was already out. Several other processors were available. And people started using microprocessors for all the small computers. There's pictures of the two guys who came up with this kit. It requires a 5-volt supply at least 100 milliamps. You can use any USB supply pretty much for this. How to use the manual. Crash course in electronics. So if you're not familiar with components, resistor color codes, identifying parts, it has that. So it's really providing insight for even the beginners. Oops. And this is really nice presentation quality paper too. They really went the full distance on this manual. Before you begin, they recommend doing the inventory of parts. They talk to you about the tools you'll need, basically a soldering iron suitable for electronics work, flux solder, some sort of desoldering capability optionally if you need it. You need a multimeter to do a couple of voltage checks, side cutters, ideally a loop or magnifier so you can check your soldering work, and optionally a pair of needle nose pliers, but that's it. a quick course on soldering. So there's several pages on that. Talks about how to bend the pins on IC so they'll fit. And then finally the assembly section. And they recommend starting by practicing with the 40 ceramic capacitors, all bypass capacitors that this board requires. And building it up with the power supply components and testing that. And then building the clock circuit and testing that. Sort of building it up in stages. Which is a nice approach. You can quickly see if you're going astray on it. And the output of this is VGA, so you'll need some sort of a VGA display device, an older monitor or something of that sort. Then it has the schematics, a flow diagram. The schematics are nicely done. All the text is in English, at least on my version of the manual. And each one, they're organized by modules, and each module has a description of what the circuit does. And then there are a couple of photos of their pre-circuit board prototype. First on pluggable prototype boards, and then when they lashed it up using wire wrap. And they even include the code for a C language simulator of the basic processor, in case you want to plug that in and simulate it. And then finally an actual Gigatron under assembly, and then the final product. Okay, so here's an overview of the parts. There's the DB9 connector for the RS-232 serial. Or is that the other way around? Let's see. Nope, this is the DB9 connector. And this is the VGA connector. There's the small 1/8 inch audio jack for the audio output. The micro USB plug. LEDs, a crystal transistor, electrolytic capacitor, auto resetting fuse, 3 47 picofarad capacitors, and then about 40 bypass capacitors, 100 nanofarads or 0.1 microfarads. A whole pile of diodes. These are 1N, well, they're BAT42s, they're Schottky signaling diodes. I thought they were 4148s, but they're Schottky types. And then a small selection of resistors, a Zener diode, and a few resistor networks. Alright, I've got all the IC sockets stuck into the board and flipped over, and I'll do my usual bit of tacking the diagonal corners of each one on there, and then inspecting to make sure they're all flat against the board, and only then go and solder all the other pins. I've got the board weighted down a little bit with some heavy tools to make sure it's laying hard against the IC sockets. And as you can hear in the background, I have a little Beethoven going on. Some of my favorite music to listen to while I'm doing long, tedious soldering projects. Alright, I've tacked the diagonal corners. Hey, no chips fell out, I got them all. time to do the real soldering. Alright, all the IC sockets are completely soldered in now. And I've gone over them with my jeweler's loupe to inspect all the solder joints, look for little splashes of solder, shorts, defects in the solder joints themselves. Now to progress with the actual instructions per the manual. Alright, most of the bypass capacitors or decoupling capacitors are installed now. The instructions recommend holding off on putting in 4 of them at the moment, and there's also a few of the 47 picofarad caps that are not supposed to go on yet, but all the other ones are soldered. Next up is soldering in the components for the power supply circuit. This includes the USB connector, a Zener diode, the so-called multi-fuse or self-resetting fuse, the electrolytic capacitor, and the part I earlier identified as a transistor. It's really a supervisory circuit, the kind of thing that forces a reset on the processor when the power supply cycles, and it does some other things. One LED and one of the resistors. Alright, the power supply components are installed at this point. Some are over here, and then the supervisory circuits down here, the power LED and its resistor. The instructions now want me to test that circuit works. The Gigatron does not come with a power supply. You're expected to plug it into some available UPS port, but in my case I wanted it to be standalone, so I bought a wall-wart switching power supply with a USB connector on it. And this one here is a CUI. I'm not sure if I can read it. I think it's an SWM6-5-NH-I38, I believe. So it's USB, and it's good for 0.3 amps, which is 3 times what the manual recommends. I'm sorry, that's on the input. It's 1.2 amps on the output, so it's fairly beefy. And the kit does come with the USB-A to, I think I said micro before, it's a mini USB plug of maybe 2 feet in length. So there's no voltage check to make here, it's just to make sure that the LED comes on when the power supply is plugged in. Let's see, do I have it upside down? I think I do. This one goes in like this. And the LED came on. So the power supply circuit is working. You may ask, as I did, why this supply needs a fuse and a Zener diode when it's getting a regulated 5-volt supply already from the USB source. And that's really just precautionary. The designers of this computer have made it as idiot-proof as they can. The Zener diode is there. It's a 5.6 volt Zener. It only kicks in if the supply exceeds 5 volts by more than about half a volt, which would get to the point where it could do damage to the circuitry. And if that happens, it basically shorts out the power supply, and that causes the self-resetting fuse to open up, protecting the computer. Next up is the clock circuit that provides the timing signals for all the components. This includes a crystal, 3 47 picofarad capacitors, a couple of resistors, and a 74 HCT04 logic chip, which I will pull from the array of chips provided. Okay, the clock circuit components are installed, and the test for this is to measure a voltage at these two test points, helpfully marked ground and clock, or CLK1. And the idea is that your average voltmeter is going to average the square wave coming off of that. And since it's a 5-volt power supply and it's a square wave, it should average out to about 2.5 volts if the clock is working. So let's try that out. So there I'm measuring it, and I'd assumed it was 2.5, but the manual says I should be looking more for about a 1.9 volt, which is pretty close, so obviously that's working. But just for yucks, I'm going to look at it with my scope. And looking at it with my oscilloscope, I definitely have a waveform there. This is on the 1 volt per scale, so it's 1, 2, 3, 4, 5, 6, 7, about 7 volts, which surprises me a little bit. There's a ground reference on the scope, and here's the incoming power supply, so I know that's got a bit of trace rotation going on, but it's basically 5 volts with 1 volt per division. And if I go look at the clock signal, it's still roughly 5 volts, but it has about a 0.7 volt on the top overshoot and maybe more or less the same below ground on the bottom. So this is not a strictly TTL signal here. Well, the instructions recommend to solder in all the ICs at this point, which would normally be a good thing because they're a lower height component, and if you'd follow the normal assembly that would work, but I've already put in sockets, so I'm going to hold off. Let's see. Since I've already put in the sockets, I don't need to solder in the ICs now. Their height is not important, so I'm going to progress with soldering in the resistor arrays. And the LEDs also get installed at this step. 3 resistor arrays and the LEDs are installed. The next assembly step is to put in the instruction decoder circuit, which is mostly done with diodes. There's 30 diodes here, the Schottky diodes, and 2 resistors comprise that circuit. Some of the diodes lay flat on the board and others stand up on one end. So all of the diodes, except for the 2 that lay flat, are bent like this with the cathode pointing up, and unfortunately my camera doesn't want to focus on it. So like that. So all the diodes in that section are in now. The next progress test on the board requires that all the ICs be installed, so even though I wasn't going to do that yet until all the resistors are in, I'm going to go ahead and do that now. I think I may have said earlier that no sockets come with this kit. There are sockets for the RAM and the EEPROM, but those are the only ones. And I wasn't really thrilled at the quality of sockets provided with the kit. They're these kind of cheap sockets. I just don't like using those. So I've already soldered in the nicer sockets, so I'm going to pull the EEPROM out and the RAM out of their sockets and use the ones I already have. And all the ICs are plugged in now. Well, there was a small unexpected development here. This power supply that I bought, the little wall wart, is supposed to be good for 1.3 amps. But when I plug it into the power test with all the chips in the circuit, I was getting this, where the power LED was flashing faintly and the power supervisory chip was holding the circuit in reset mode, indicating that it did not have enough voltage, or it was unhappy in some way with the power supply. And with my oscilloscope set up on a 1 volt per division, I'm just measuring across the Zener diode here, which is across the input power. And it's only showing a little over 4 volts. Oops, it sagged. Let's bring that back up. Anyway, it's only about 4.5 volts. That may not be enough to satisfy the supervisory circuit. And so I was wondering if the power supply was good. It should be putting out more than that. None of the chips on the board are warm. So I disconnect my scope. And I have my bench power supply set for 5 volts. I disconnect the USB supply, and I just clip on to the input side of the fuse. Let's see if I can get it on there good. And the negative side of the Zener diode, and turn that supply on, and voila! I get a steady power LED, and the blinking lights are blinking, which indicates that the board is alive. And it's only 74 milliamps that's being required by this, which is well below what the power supply should be good for. So I think there's something wrong with my USB power supply. The board seems to be working just fine when provided with a functioning power supply, and it's not like it's sucking a lot of current. It's well within the 100 milliamp specification. So going back to the test that I was supposed to do before I ran into that little snag, I've realigned the power supply plugs so they're not in the way of the LEDs, and I'm going to turn the power supply back on and make sure I do have the right activity. Got the test pattern. That's definitely intelligence behind that. That's not random activity. It's got to be working. Well, I've been working on this all morning, and I think it's time to take a break for lunch. Well, I had another bright idea before I went out to lunch that's a pretty reliable power supply I've got there. That CUI brand has always been very reliable to me, and I wondered, this little USB cable they give you with the kit doesn't feel like it's the greatest quality ever made. It's kind of cheap looking. So I grabbed just a generic longer USB cord that I had laying around, and look at that, it works. The problem was the cable, not the power supply. I'll have to let the guys in the Netherlands know about that. Well, we know the computer works because it flashed the blinking lights, but to get it to do something more useful, it's necessary to add some I/O to it. And this is all done through the various connectors, such as the audio output circuit and the video output circuit. So, starting out to do that, we'll put in the parts for the audio output. For the audio circuit, we need the audio output jack, a resistor array, and a single discrete resistor. And so that set of audio output components are now installed. For the gain controller, the DB9 connector is required, and one more discrete resistor. And so now that's installed. And the remaining thing to do is to assemble the components that generates the VGA video output. And because this is a color output, it's going to have to send an analog signal, which is going to specify the different colors. So it's going to need, looks like 8 resistors and a connector. And here are the 8 resistors and the VGA connector. And there are those components installed. So the board looks like it's complete now. Okay, so now it's ready for a full-up test. And I've got this little, like $40 miniature monitor, which and a pair of computer speakers. So I'll turn the monitor on. Give it a moment. It's connected through the VGA connection to the computer here. Okay, I'm going to plug it in here. See what we get. Gigatron 32K TTL microcomputer ROM version 1. And I've got my game controller here, and I can move the cursor up and down. I don't know what happens when I move left and right, apparently nothing. It says use up and down to select, press A to start program, where there is no button labeled A on here. Hold the start button for reset. So what happens if I push the up button? Nothing. If I push the right button, something happens. Alright, I don't know how to play this game. Oops. Okay. Get ready. What do I push? Anything I'm pushing is resetting it. Nope. Says it's in auto mode. That's not it. Oops. I don't even know what the goal of the game is. Okay, that's not doing anything. Left and right doesn't do anything. Maybe it's these cursor buttons. Ah, there we go. Maybe the goal is to keep from hitting the side of the screen. Maybe getting the hang of it a little bit here. Can't hit the border. I guess the idea is to hit all the different little green squares without going out of bounds. That would seem to be the... or hitting the same place you already hit, I guess. Alright. Well, I think you get the idea. And if I push the start button and hold it, that resets me back to here. Let me select the racer. I don't know if it's apparent on the screen here. There's two different quality settings. 3 or 4 scan lines on the screen, and then there's a blank one that's just black. And if I push the select button on the remote control, it toggles that. My understanding is that because the video is bit banged on this computer, there's no video chip, it's spending a lot of its time just processing the video and needs some time to actually execute code. So it doesn't bother every 3rd or 4th or 5th scan, whatever it is, and where it's blank there during that scan time, it's busily executing the code to update the screen. And you can turn that off to get better video quality, but then it runs a lot slower. Alright, so the left and right cursor moves the car left and right. The up and down doesn't seem to do anything. The top button on the right doesn't seem to do anything. Oh, there we go. That's the throttle. I can go to credits. This Gigatron TTL computer kit was conceived, designed, and brought to you by Marcel van Kervink and Walter Belgers, based on an original design by Marcel van Kervink. I'm probably mispronouncing that. Thanks must go to Mark, Paul, Ivan, Ivana, Oscar, Martin, Eric, Bella, etc., etc. Okay. So let's go to pictures. Look, I keep hitting the wrong button. There, pictures. It should be doing a slideshow here. I don't see any button that makes it advance the picture sooner. Seems to not regard the left buttons at all. So there's really just 3 or 4 pictures there. And reset. And select Mandelbrot, which should be a fractal program of some sort. So I don't know if it's apparent, but there's a line being slowly drawn around the periphery of the screen. This computer running in the way it does obviously is not a speed demon. It's running with minimal resources, but it does seem to be functioning perfectly. So it's doing a lot of calculations here in order to display the fractal or Mandelbrot images. It's going to take a while to get there. So as the Gigatron is, It can play a couple of games, it can do the Mandelbrot, it can display a small library of pictures, and that's about it at the moment. Obviously it's firmware driven, and it's on version 1 of the ROMs, or the firmware. It seems likely that there may be some sort of an upgrade for this in the future that would maybe allow it to do a little bit more. I was thinking that this was an RS-232 port that's on there, but I don't think it is. I didn't see any chips in there that would actually generate RS-232. I think it is a dedicated port just for that game controller. So as such, without a USB port or a RS-232 or something, it doesn't really have any meaningful I/O to hook up to anything else. It's really dedicated to doing the things that are in the firmware, and as such it's a demonstrator primarily. However, it is in theory programmable, and different applications that do not require hooking up to a lot of external stuff beyond what it's already designed for could be written in the code that this is capable of executing. But I don't think you're likely to see this thing running BASIC or C or anything in the near future. I may be totally wrong with that. Something clever could be in the offing. It's rather interesting to note that when it's working on the simpler parts of the pattern, the little cursor you can see in white going in a clockwise direction around the rectangle seems to be moving along pretty quickly. But when it gets to the area where there's a lot of action going on, you can see it slows way down, like right about there. And then it speeds up again. I'm presuming that's the area of maximum calculation density, and it's spending more time doing the math. That would be my guess. And I haven't been paying attention, but I think that digit in the middle is counting minutes. While it's doing that, I'm going to put it in its case. The back side is unfinished of the wooden box, but it does come with a set of little rubber bumpers. And it already has the cutouts in the back, so I should be able to just lift the board and set it in there. It needs to actually go through the holes. There are enough of these little bumpers to put a bumper on the back corners of the circuit board, way out in the corners. And the case seems to allow for those to be used. Okay. So connecting the audio back up and the USB power, I'm going to execute the Mandelbrot again. And here is the cover with its plexiglass. So it comes out very handsomely. So with this, I'm going to step back and just let it do its math. While it's doing that, I had an email from one of the originators of the kit. I pointed out that there was a problem with the VGA cable, and he asked me what kind of voltage am I getting when I'm running it through my own cable. It's still a little bit south of 5 volts, but it's higher than it was with their cable. So it does look like it took roughly 20 minutes, just a little bit less than 20 minutes to do the image, and now it's started on a new one while I was in the other room. So you can just let it sit there and do this all day long. On the last printed page of the manual, it does describe that the game controller that's provided with the Gigatron is the Famicom controller. So even though the printed manual that came with my Gigatron doesn't really describe the game controller in any detail, nor does it tell you how to play the games or other applications, there is a page on the Gigatron website. So this does describe the Famicom-like game controller, and it describes what the buttons are. The A button is the bottom one, and there's a B button, and then the other two are just auto repeats of A and auto repeat of B. So the start button is used to do a soft reset by holding it down for 2 seconds. It stops the current application and returns to the menu. The select button switches the retro scan line on and off. I already showed that in the video. So obviously applications run faster when the retro scan line modes are enabled, and some only work well in that mode. And then the button cluster on the left is the one you actually make menu selections with and navigate for the games. The menu is actually reporting the amount of RAM that it finds, so that's a real number. It's not just some static thing, it's actually looking at all the memory and reporting it. The snake program is described here, It runs across the screen and can't stop. Use the arrow buttons for changing its direction. Green blocks are food and must be eaten. Each time the snake grows a little bit longer. Orange blocks are poisonous and must be avoided. Don't hit the walls and don't bite your own tail. Those are the rules. There's a countdown timer for scorekeeping. If you eat food before the counter reaches 0, the remaining seconds will be added to the game score, and 5 seconds are added to the timer with a maximum of 15. If the counter reaches 0, the next food won't give any points, but it'll increase the timer. The game starts automatically. If the player doesn't change direction before reaching the first wall, the Gigatron plays the game by itself. I didn't see that happen, but I wasn't looking for it either. In the racer, you control the car. You steer with the left and right arrow buttons. The A button accelerates and the B button brakes or slows down. Be careful to stay on the track. The objective is to complete laps as fast as possible without hitting the curbs. Mandelbrot. This application draws many views of the Mandelbrot fractal. Intriguing and endlessly complex figure that emerges from a simple mathematical formula z squared plus c. The clock in the center counts hours and minutes. It's a 24-hour clock. You can set it by pushing the A button and holding it down. The color changes to yellow, and then you can use the arrow buttons to set the time. Use the left and right to change hours, up and down to change the minutes. Shortly after releasing the A button, the color changes back to white, and the colon stops flashing once the clock is reset. The pictures converts the Gigatron into a picture frame. ROM version 1 comes with 3 classic, colorful, high-resolution images built in. These are ones that I remember seeing as demonstrators on early color computers, personal computers. So in that sense, they are classic. Every 15 seconds, the next image is shown. You can hold down, I guess, apparently any button if you want to look at the image for a little bit longer. And then there's the credits. And here's the loader. The loader listens to data packets on the game controller port and stores them in memory. If you hook an Arduino up to the controller port and send commands or complete new programs into the Gigatron this way and run them, detailed instructions are soon to follow in the tutorial section of the Gigatron website. I didn't demonstrate the loader, but it is there on the menu. So that answers that, and because data packets can come in that way, presumably that's how you could connect a keyboard if you wanted to generate and load in a keyboard related application. So in short, that answers the question I had earlier about there not being any I/O for hooking up anything else. And as this clarifies, if you have an Arduino and it can provide the data packets that the Gigatron requires, you can manipulate RAM and load entire programs in and run them. And through the Arduino you should be able to connect other I/O in the same fashion, and presumably keyboards and so on would be possible that way. That's more than I'm really interested in doing, but I'm sure many hobbyists and hackers will have a ball with that. Since I really like hard copy manuals, I've taken the Gigatron website's brief user manual and just did screen captures, dropped them into my page layout program, and from that I have a 7-page hardcover manual that I can access anywhere without being near my regular computer. And I can keep it with the assembly manual. If I had one criticism about the manual, I would say that since the assembly manual is so beautiful, it'd be nice if some version of the user manual were incorporated into it instead of being just a download. Of course, having it as a download allows it to be updated more readily. I always understand that, but still. Now that I've got a little better idea how the applications work, I'm going to review them one more time just before closing out this part of the video. Right, so I hadn't shown the loader yet, so let me do that first. So in this mode it is ready to load in either data or applications through an Arduino that's connected to the game controller port. So I'm going to reset from that. 2 seconds on the start button, and it does reset and plays the fanfare. Going back to the snake. Now that I know the rules, I probably still won't be coordinated enough, but I'm going to let it play the game itself. So it's in auto mode now, as indicated by this. So now I'm going to try playing it. Oops, oh! I'm too slow-witted with too slow reflexes. Well, I think you get the idea. And so with the racer, so A is faster and B is slower. The manual says that B slows it down. I find it does nothing. Or I'm sorry, I'm using the wrong button again. Yeah. The B button does break it. It doesn't slow it down, it doesn't decelerate it, actually stops it immediately. And B just hard stops it. Ah! Oh, I see. If you don't hold the A button down, it gradually decelerates. Okay. I was skidding a little bit there. Okay, that's better. Now it's more of a game. Okay. Now it's working. I get the drift of it. I don't think we need to see the Mandelbrot work again, but I do want to play with the clock very briefly. So let's try that. So I want to set the clock. So I'm holding down A, and it changes the color to yellow. And then left and right should change the hours. Okay, there we go. And then up and down should change the minutes. So I've set the time. So that works. And once again, if I go to the pictures, it should be about 15 seconds per picture. Should be about now. There it goes. That's 5 seconds. It's about 10 seconds. Anytime. There it goes. Yeah, pretty much exactly 15 seconds per. So that's all great. And it's just got those 3 pictures. Oops. Yeah. I wanted to press the select button to change the video quality a little bit. There we go. Not all that noticeable, but you can see that when I put it in that mode, it slows it way down. Seems to make the picture a little brighter. I think because it's filling in more of the scan lines. Anyway. So as with many of my other little documentaries on electronic equipment, I'm going to conclude with an overview of the schematic. The incoming power comes in on the USB. It has a test point and the self-resetting fuse here. There's your Zener diode, kind of crowbarring across the power after the fuse, across the power supply after the fuse, so if the voltage is too high, it'll cause that self-resetting fuse to open up for a while. And you have your single electrolytic capacitor there for filtering, and then all of the decoupling capacitors are all just wired in parallel throughout the circuit, and you basically have your VCC and ground. The oscillator circuit is a classic oscillator, a couple of capacitors, a crystal, 2 resistors around an inverting element. Then you've got a buffer, and then 2 of them in parallel acting as a booster, and that gives you your clock 1 signal. And then there's also a delay line with 2 inverters and a capacitor, which is used for the user registers AC, X, Y, and out. This 47 picofarad provides an additional clock 2, clock 1 shift of 5 nanoseconds, which is required when using the original 70 nanosecond SRAM at 6.25 megahertz, or when overclocking in general. It is not needed when using the 55 nanoseconds SRAM module at 6.25 megahertz. Here's the supervisory chip. VCC and ground are connected to it, and it's essentially providing a reset line, low to reset, which resets the program counter and either just resets it or holds it reset, thereby preventing the computer from running. And it does that when it's at a logic 0, but when it's a logic 1, in other words not reset, then it energizes the LED through its resistor. So the power LED is complementary to the reset. And that was what we were seeing earlier on in the video when it was flickering. It was right on the hairy edge, apparently, of what it considered to be a valid power supply voltage. And it was just sort of chugging along right on the hairy edge. And I did have a email communication with the creators of this kit saying they did have some issues with voltage drop in the little USB cables. they're furnishing. Apparently it's not usually a problem, but they're looking into that further. Nice thing about it is, even if you get one of these kits that has a flaky USB cable, the things are practically free and ubiquitous everywhere you go, so you don't rely on that as a critical part. This logic here with these 4 chips and these other chips, this forms the 16-bit program counter, or PC, which normally increments by 1 for every clock cycle. Conditional branches can go to any location within the current 256-byte page. Unconditional jumps can go to any location in program memory. When there is no branching, the memory space is linear, and the program counter will cross page boundaries. This is the control unit, which deciphers the instructions so the rest of the logic knows what to do with them, and that's achieved by all this diode logic here and here, as well as, you know, some of the buffers and inverters and so on surrounding it. The control unit expands 8-bit opcodes to 19 control lines. The schema is orthogonal. Bit 0 and 1 control what is on the data bus. Because you've got 2 bits, it can be 4 different possibilities. One of those is operand, another one is RAM, another one is accumulator, and the other one is input. So the lowest 2 bits of the opcode determine which item is on the data bus of those 4 choices. The next 2, or bits 2, 3, and 4, select the addressing mode during operations, or the condition during branches. Bits 5, 6, and 7 determine the operation performed by the arithmetic logic unit, or ALU, and the type of instruction. This next block says, for speed and simplicity, the memory addressing space is 2-dimensional. The address unit can create addresses in 4 different ways, as shown in the table. And there's the table. I won't explain it right now, but they do pretty good descriptions here. The low address byte originates either from the operand D or from the user X register. The high address byte is either 0 or comes from the user Y register. This unit is the equivalent of 2 large 4-bit 74181 ALU chips that were at the heart of many 1970s microcomputers. This design is inspired by Dieter Müller's excellent notes starting from this website here, which you can read and explore at your leisure. The next block is, besides the program counter, there are 4 user registers, AC, X, Y, and out. Each has 8 bits. AC is the accumulator for calculations. Registers X and Y are used to form memory addresses. Y is also used by the jump instruction. Out is the primary output register. Only AC can write back to memory. The others are effectively write-only. Or should that be read-only? And then the last page of the schematic. The out function gives 6 color bits and 2 sync bits for VGA. X out is the extended output register. X out is controlled indirectly through the inverted H sync and AC. On a positive edge it clocks in AC. X out drives the 4 blinking lights and a simple 4 bits audio DAC. The waveform comes from software. The inverted H sync and inverted Y sync double as clocks for the game controller and receiving shift register. So I don't think I have much more to say about this kit. I will make a brief mention of the monitor I'm using here. I selected this because I didn't have a VGA monitor anymore, and I wanted something small just like this computer, and this was the closest thing I could find. This is the kind of thing that's intended probably to go in motorhomes and things like that. It's intended to be mounted on a wall and probably in a fairly confined space. It has two little speakers on the back, and it does have jacks for composite video. There's a BNC connector. I think it's HDMI. There's VGA. Practically any video signal you could hook up can interface with this little monitor. And it does have a remote control for changing its settings, and a versatile mounting system. And because it has so many input modes, you can use it with practically anything that you might want to display. And there's a lot of these out there. I just picked this one mostly because of its reviews on Amazon and because of its physical size. I thought it would be a good mate for this for display purposes. As some evidence that there's a lot of expandability possible by at least going through an Arduino and into loader mode, here's a YouTube video that's already been put up. I'm just shooting this right off my screen. So there's the Arduino hooked up. Going down to loader mode, and already there's text being typed to the Gigatron from the external Arduino. So there's a proof of concept there. And I have an email from one of the creators of the Gigatron that one of their more immediate projects is to indeed come up with some sort of a programming language, something like BASIC, and a means to interface at least a PS2 type keyboard without having to have an Arduino. So there is work being done on that, so presumably some future expandability is going to be possible with this device. Here's just a little bit more from the website. I just keep adding stuff. Can't finish the video. The EEPROM contains all software described on the online user manual, but if you want to experiment yourself, don't want to erase and reprogram the EEPROM, the loader application will allow an external device to load new data, programs, and commands into the Gigatron RAM. We prefer to use an Arduino as an external device because that is the most flexible. You can use 4 male to female jumper wires to hook it up as shown below. The Arduino then acts as a bridge between your computer and the Gigatron, giving you an easy way to use its keyboard and storage. So there is all sorts of stuff on here for the hacker and hobbyist. And there are some videos available. So, more to come, I guess. And I promised to show where I got my monitor. This is the Lancevon or Lancevon, or I don't know how that's supposed to be pronounced. 10.1 inch small portable computer HDMI VGA HD LCD monitor display screen. Good for the Raspberry Pi 3 HD, is that Pi 3? HDMI monitor screen, CCTV application, security camera monitor, 1024 by 600, video, audio inputs, built-in speaker. It's $75.99 on Amazon. So just a quick overview. So it is 1024 by 600. Good for security surveillance. They have another item that has higher resolution. It supports NTSC and PAL. Works as a Raspberry Pi 3 computer monitor screen, compatible with Sony camera receivers, HDMI output. Works with all sorts of Windows operating systems, from Windows 95 up through Windows 7. It has English, Chinese, French, Italian, German, and Spanish languages. I'm not sure. I guess that just means it can handle the characters. I don't know what that means. It's not explained. Monitor works perfectly with a card, DVD, surveillance camera, STB, satellite receiver, other video equipment. The package includes the TFT LCD monitor, one VGA cable, one 12-volt DC adapter charger. It's not really a charger because this thing has no battery in it, but it does come with the AC powered wall wart to power it, or you can use a cigarette lighter type power cord, which also comes with it. Has a remote control, one bracket, one sticky panel that you can use to stick it to a surface, and the half of a page of paper user manual. So there again is the description if you want to pursue getting one of these yourself. That's all I have to say on that. Hope you enjoyed the video.